Good morning, Astronomy 1020. Welcome to our fifth lecture of the semester. Today, we were going to spend even more time analyzing the nature of light and learning about how light is created inside the electron orbits of atoms. If there's time, we'll even review that concept of power that we got a little taste of in our last homework session. And eventually we'll want to move on to talk about large-scale properties of light and how hot glowing objects like stars emit light. But first, let's start by reviewing some of the things that we learned about having to do with atoms. In particular, I'm thinking that last class I taught you guys about the Bohr model of the atom and some of its properties. You might want to open that up in your notes here. I did not have time to test you to make sure that I really believe that you understand. So why don't we try a little sort of show and tell test here. Why don't we play a game called Let's Build an Atom. And the atom that I'm thinking of has an atomic number of 1, a mass number of 1, and is electrically neutral. Who can use their notes while I adjust the blinds and help me build that atom? I suppose if no one volunteers, then I could look for a volunteer.
The atomic number is the number of protons in the nucleus.
Okay, Nick, so tell me how many protons this atom has.
1. Oh, no, 2. Sorry. Nope, it does have 1.
Okay. You sure?
Yeah, I'm sure. Because there's 1 right there.
All right. The mass number is 1. What does that mean?
Are you asking me or somebody else?
I'm asking you since we're talking.
Okay. All right, cool. No problem. The mass number is the number of nucleons in the atom, which is the number of protons and neutrons.
So how many neutrons does this atom have?
1? Or it'd be 2.
Hold on a second. The mass number is the number of nucleons.
Yeah.
What's a nucleon again?
I may have missed that in my notes.
You just read it to me 50 seconds ago. No, 20 seconds ago.
The atomic number, you mean?
The mass number.
Mass number is the number of nucleons in the atom.
Keep going.
So the number of protons and neutrons.
So you just read me what the definition of a nucleon is, right?
No, it would be 1 because the mass number is 1.
No.
Right.
Hold on. Rather than answering the question that you're trying to answer the question that I'm asking you.
Okay.
I need to know what the definition. You need to know what the definition of.
I'm having trouble recalling the last lecture, so I'm just literally going by what I wrote here.
Right, but I guarantee you that you did write down what nucleons mean when we built our helium atom. But also, I included the definition of nucleons right in the definition of mass number. You've now read it to me twice, but you've read it to me quickly, and you haven't been thinking about it. So read that definition of the mass number again.
So it's the number of nucleons in the atom.
Which is the same as?
The mass number.
No, what does it say on the next line?
Number of protons and neutrons.
The number of protons plus
the neutrons. Okay, that's what I was missing. I was missing the little plus signs there.
Sure, or and is plus too, but nucleon means proton or neutron. So how many nucleons do you have so far?
1.
Okay, and how many nucleons are you allowed to have?
1 because the mass number is 1.
So how many neutrons are there?
1. Maybe I'm not understanding the question.
Oh,
I think you should call on somebody else.
Nick, that's okay. Everyone would go through the same thing you're going through. Trust me, I've done this a million times. You have to do this. How many nucleons do I have now?
2.
Is that how many I'm allowed to have?
That says 1.
So something's wrong here. We got to fix it.
Oh, you have 2 there. I'm gonna
You're gonna
phone a
hide?
friend here.
Does anyone
Yeah.
understand what's going on? See, they don't get it either, Nick. They're just
Okay, I feel a little bit better.
yeah, they're just as lost as you. It's not like any of them understand. You're the only difference is you're trying. Okay, right now you have 2 nucleons, but you're only allowed to have 1 nucleon. What are you going to do to fix that, Nick? You're going to get rid of one of your nucleons.
Okay.
Choose one to get rid of.
The neutron.
Okay. So now we have 1 proton and we have 1 nucleon. How many neutrons does this atom have? Nick?
Okay, so I got the atomic number part here. Does nobody else wanna sub me in here?
No, they don't, because they don't get it. They don't get it, Nick. What you're doing is noble. I just asked you a simple question. How many nucleons does this atom have?
1.
Sorry, right. And how many neutrons does this atom have?
So that mass number is the number of protons or neutrons.
It's the
Correct.
It's the total number of protons plus neutrons.
There's so many names, and I have so many different names, and I have a drawing, a really awful drawing of an atom here. So I can't really
Would it be 2?
If I put in 2 neutrons, then how many nucleons would I have? How many nucleons is that? Why can no one answer me a simple fucking question? How many nucleons is this?
3.
That's 3 nucleons. Are you allowed to have 3 nucleons in this atom? No, you're allowed to have 1. So that's not right. I just want to know a simple answer to a simple question. How many neutrons does this atom have if its mass number is 1?
Would it be 1?
If it's 1
Or none.
neutron, then how many nucleons do you have?
2. Okay, so would it be none?
That's the right fucking answer. Right. It's no neutrons because you've already used up your 1 nucleon. The mass number is the total number of particles in the nucleus. You have 1 particle in the nucleus already, so you're done. There are no neutrons. People think this is the number of neutrons. It's the number of protons plus neutrons. If you have 1 proton and your mass number is 1, then you're done. Okay, I hope we all learned something there. How many electrons does this atom have?
I'd say 1,
How do you know 1?
because it has to be neutral.
That's right. And neutral means same number of positive as negative charges. This is your atom. It's the most famous atom in the entire universe. It's the most abundant atom in the entire universe. What is the name of this atom?
Hydrogen.
That's right. It's a particular type of hydrogen. Can you tell me what type of hydrogen it is? It's got a
Atomic weight is 1. It's not deuterium or tritium.
It's the other one.
Isotope.
What's the isotope that has 1 proton and no neutrons?
I know the other 2, but I have no idea what this one is.
Yeah, that's this one. It's rare to know this because normally people just call this one hydrogen, but this has a proper name. It's called protium.
All right.
Protium is the most common form of hydrogen. Okay. Wow, we sure needed some practice. Let's build another atom. Okay. This atom has an atomic number of 1, a mass number of 2, and is also electrically neutral. Now I'm guessing this time you'll be a little better at this. Nick. Nick, how many, come on, let's prove you've learned something here. You can do this, you can do this. Nick, how many protons does this atom have? Nick, just turn his video off. Okay,
You got ghosted.
come on, Mariah. No, try it, Nick, come on, see if you learned something.
I'm just gonna watch it for now because I need a refresher. I'm not gonna put everybody through that. So
Okay, well, it's not that everyone was going through that, whether you were answering or they were answering, Nick. To somehow believe that they knew the answer and were sitting there silently, you're dead wrong. They were all just as lost as you. I know this. That's why I asked these questions. Mia Femino, you're going to help me build my atom.
That is a bad idea.
How many protons does this atom have?
This is a bad idea.
Why don't you just read the definitions of these? See, you guys don't know shit. You don't know anything. That's why we have to fix that. Read me what the atomic number means.
Tells you the number of protons and it defines.
How many protons does my atom have?
1.
Right, because A equals 1. Okay, here we go again. I need to know how many neutrons this atom has. You have a mass number of 2. What does the mass number mean?
The mass number is the number of nucleons in your atom and the number of protons plus the neutrons.
That's right. So the number of protons plus the neutrons can be 2. So how many neutrons does my atom have?
2. Or it'll only be 1.
Which is it?
1.
1. Now, if I add 1 neutron, I have 2 nucleons. Good. How many electrons does my atom have?
Wouldn't it be none because you already have 2?
I have 2 nucleons, one of which is positively charged, the other of which is neutral. This atom is neutral, but it currently has a net positive charge of +1. That's not okay. That's not neutral.
So you need 1 negative.
Okay.
Cute question, or am I right?
Wait, I don't understand what you just said because I didn't hear it.
Sorry, there's a lot of background noise going on in the street.
You sound
Can you
great.
repeat the question again?
You sound crystal clear. I don't hear any of the noise. I just
Okay.
hear you.
Can you
I'm just
repeat
trying to
the
get you to tell me how many electrons there are, Mia. That's all I want to know.
1.
That's right. Because 1 electron cancels out 1 proton to make it electrically neutral. Neutrons don't affect the neutrality of atom because they're already neutral. What's the name of this atom? Well, we learned in our discussion on atoms that an atom is defined by what? Go ahead and read your definitions of these things. Which of these numbers defines what the atom is?
The atomic number.
Okay, so why would I expect you to know the name of this atom if its atomic number is 1?
Would it also be hydrogen?
That's right, because the atomic number defines the atom, and if it's the same atomic number of 1, the same number of protons, it's still hydrogen. The difference is it's not the same isotope of hydrogen. What's the name of this isotope? Someone was bandying some terms about a moment ago.
Deuterium.
Deuterium.
Oh, deuterium. Okay. Not sure about pronunciation.
One of the most common isotopes found in nature. Deuterium is another flavor of hydrogen. It's another isotope. The difference is that deuterium has 1 neutron and hydrogen has no neutrons. Okay? But they're both hydrogen because the number of protons defines the atom. Let's see where we might find some hydrogen. Let's take a trip to outer space together. Let's go somewhere fun. Like, I don't know, the Eagle Nebula. The Eagle Nebula is a massive structure of mostly hydrogen and helium gas found somewhere out there in the disk of our galaxy. If you could fly through all this stuff in the Millennium Falcon and scoop up pockets of this gas, you would discover that this gas is made up of 70% hydrogen and maybe 28% helium. So that means, because helium is heavier than hydrogen, roughly for every 9 hydrogen atoms that for every 10 atoms that you counted up, 9 of them would be hydrogens and 1 of them would be heliums. So there's 1 helium atom to every 9 hydrogens.
Wait,
And there's yep.
sorry. So the percentage is calculated not the
By
amount
number,
wise,
but by
mass.
mass. That's right. You can calculate, and this is an important question to ask. You can calculate the percentage weight of the gas by mass or by number of particles. It's common to do it by mass for reasons which have to do with interest in stellar formation. But if hydrogen makes up 70% and helium makes up 20%, remember we drew a helium atom last time, Vladimir. Helium had 4 nucleons, 2 protons and 2 neutrons. That makes it 4 times as massive
Than protium.
as a protium, right? So basically, if the ratios are 70% hydrogen to 28% helium, that if you do the little algebra problem, which just takes a second, it turns out to be 9 hydrogens to 1 helium is the right mixture. Let's imagine that we counted up a whole bunch of atoms of gas in the Eagle Nebula, okay? And we only focused on those 9 hydrogen atoms, and every 10th helium sorry, that's not 10th helium. Every 10th helium we flicked out back into space. If we built up a big bucket of just hydrogen atoms, we would discover that some of the hydrogens were actually deuteriums. And the abundance would go something like this. For every 6,000 protium hydrogens, you would find 1 deuterium. And you would find this everywhere you went in outer space. That deuterium was naturally kicking around, but in a ratio of 1 to 6,000. And this has a very important name in physics and science. It's called the cosmic abundance of deuterium. The cosmic abundance of deuterium, 6,000 to 1, goes all the way back to the beginning of our universe in the Big Bang. This is a leftover record of how our universe formed. In fact, my cup of iced tea here is mostly made up of water molecules. And you all know what a water molecule is made out of, right? What's a water molecule made out of?
One atom of oxygen, 2 atoms of hydrogen.
Very good. Okay. And normally, under most circumstances, typically those water molecules have protiums stuck to them. Hey, Vladimir, since you know so much about atoms, I got a question.
Hit me.
What force of nature makes the hydrogens want to stick to the oxygen?
Okay, so
You've got 4 forces to choose from. You've got a 1 in 4 chance of guessing correctly.
I mean, it's not exactly guessing, I have to think. So, okay, not gravity, cross out gravity.
Good.
So there is electromagnetic force, which is inside the atom, so that's crossed out as well. So it's something between the atoms. I'd say it's one of them, so strong nuclear force, one of them holds the atom itself together, the other one,
I don't expect.
Actually, no, I'll go with the electromagnetic force.
Correct. Nicely done. Okay, except I agree with you. This molecule is held together by electromagnetism. But do you want to know why that's confusing to me, Vladimir?
No.
This hydrogen has 1 proton and 1 electron, so it's electrically neutral.
Yeah.
This oxygen atom has 8 protons, 8 neutrons, and 8 electrons, so it's electrically neutral. Normally in electromagnetism, things want to stick together because there's like an imbalance in positive and negative charge.
Yes.
So why would a neutral hydrogen want to stick to a neutral oxygen?
Because it's electromagnetically, it's energy-wise, it's very profitable if an atom has 8 electrons in its outermost shell.
It already had 8 electrons.
But
you
it's not on the outermost shell. It,
Oh,
it
yeah,
has
okay.
6 electrons in
Okay,
the
okay,
outermost.
fine. I'll give it to you. I'll give you that. Okay. The real reason.
Is there another reason?
Well, there's a reason. There's a reason that's the same reason, but there's another way to think about it. So you're thinking like a chemist who has rules for how many electrons you can have in each shell. Let's think now like a physicist instead. Here's how we think like a physicist. Electrons, negatively charged, are negative particles, and they hate each other. And all they want to do is get as far away from each other as possible. So if you're an atom that has 8 electrons, that's kind of like being a house with 8 dogs running around your backyard, and those dogs are all going to fight with each other, right? Now your neighbor has a smaller house, and he only has 1 dog in his backyard. And the neighbor on the other side has 1 dog, and he's got a small house too. What if you opened up the fence between all of your houses? Then all 10 of these dogs could run around everybody's backyard, and they wouldn't be fighting so much because they'd have more room to roam, right? The electrons can achieve a lower energy state and spread out more. If they have more territory to roam, it lets them get a little bit further away from each other. However, the dogs will tend to run around the biggest backyard, and all these electrons will feel the greatest attraction towards these 8 positive charges rather than these individual positive charges. This, of course, makes the electrons preferentially hover around the oxygen, and this gives the water molecule a secret little polarity. It's known as the dipole moment of water molecules. And water molecules are like little boomerangs that have a slightly negative side on the front edge and a slightly positive side where the protons are exposed at the back. And this little difference in polarity is what makes water so magical. It's why water can dissolve salts and why your body is basically just a goo bag full of water that can dissolve salts for energy. It's why the Grand Canyon can be stripped away and chipped away at time. Even rock is susceptible to this polarity of water molecules. The electromagnetic force will slowly rip away at the rock and carve out a Grand Canyon. Water's polarity truly makes it a miracle molecule. Anyways, wouldn't you be surprised to know that even in a big glass of water like this, 1 molecule of water out of every 6,000 is not H2O, but is actually HDO. It's a water molecule that has an oxygen, a hydrogen, and a deuterium stuck to it. Even the cosmic abundance of deuterium finds its way into our glass of water after its formation in the Big Bang. If you search long enough in my glass of iced tea, eventually you'd find D2O. And D2O is what we sometimes call heavy water. It's an oxygen with 2 deuterium stuck to it. Chemically, it's the same as water. You can drink it. You wouldn't want to drink a pure glass of it because it would be heavier than water. You'd probably feel it in your gut. Sometimes they do these experiments. I read about one where they fed a dog 7 liters of deuterium-laced water, and it got sick after that. But then again, I think anyone would get sick if you fed them 7 liters of water. So I'm not sure how that actually works, but it sounded like a cruel experiment nonetheless. The point is these isotopes, the atoms that have isotopes are all around us, and they form naturally through processes that I can't explain to you just yet, but they're there. Isotopes occur naturally in nature, and they just have differing numbers of neutrons. As Vladimir suggested to us, there's even another more rare version a rarer isotope of hydrogen called tritium. And tritium actually has 2 neutrons stuck to it. I won't go into that now. Okay, so now you know a little bit about protons and neutrons and electrons. One thing that we might not have had time to talk about, but it could be an important issue, is that nature is pretty bizarre in her construction of protons, neutrons, and electrons. And let me give you a sense of how this works, okay? Let's say we compared our 3 favorite subatomic particles. So we'll make a little chart here. I think I forgot to do this last time, so I'll include it now. These are some useful things to know about protons and neutrons and electrons that would be helpful for you guys going forward. Clearly, you don't know too much about atoms. I determined that by this most recent discussion, but that's okay. You're capable of learning, I hope. Okay, so let's draw a proton. I'll make it a big fat particle. Let's draw a neutron. I'll make it a big fat particle. And let's draw an electron as a little tiny particle. There's a reason I'm representing them like this, okay? I want to compare 2 of their properties. I want to compare their mass to the charge. Mass is a property related to gravity. Charge is a property related to electromagnetism. As you by now know, the charge of a proton is +1. The charge of an electron is -1. And the charge of a neutron is 0. That means, in terms of charge, electrons and protons are equal but opposite. They balance each other out in terms of electrical neutrality. But in terms of mass, it's just not the same. Now, the mass of an electron is a pitifully tiny number. The mass of an electron is 9 times 10 to the negative 31 kilograms. But so what? We're not talking about bricks here. We're talking about electrons. They're microscopic little nothingnesses of matter. They're little dujicles of matter, just hardly even a little thing at all. Rather than try to compare these things in terms of kilograms, which is going to get hard to understand, let's refer to the mass of an electron as 1 electron mass. In other words, the mass of an electron has the mass of an electron. If you tried to compare the mass of a proton to the mass of an electron, you would discover that the mass of a proton is approximately 2,000 times greater than the mass of an electron. And weirdly enough, this is pretty strange, the mass of a neutron is also approximately 2,000 times greater than the mass of an electron. That means neutrons and protons are like big fat particles with roughly the same mass, and electrons are little rinky-dink particles with hardly any mass at all. This is why the mass of an atom is not really affected by the electron. The mass of an atom is affected by the protons and the neutrons, but the electrons don't matter in terms of mass. They matter a whole lot in terms of charge. My question is, why is nature so perverse in her design? Why did nature, and how did nature, make this big fat particle that can be battled equally by a little tiny particle, a sort of David and Goliath done out in the nucleus of an atom, or I guess in the internal structure of an atom, where a proton's charge could be balanced by a particle way more microscopic. The mass is a totally different thing. In fact, it's going to turn out that nature can sometimes reverse the process. Nature can build antimatter particles, little tiny dudes that have positive charges, and big fat dudes that have negative charges. Those are possible as well. But you must realize that there's this weird asymmetry between charge and mass within the atom. Okay.
So could it be that they're unrelated?
Could it, I'm sorry, say that question again, because it interests me.
So could that be that the mass and the charge are unrelated? Because I was about to ask you how come they
Wait,
have
did you say could they be related or could they be
unrelated? Unrelated.
Well, as far as we know, they are unrelated. The mass is related to gravity, the charge is related to electromagnetism, and we don't know that there's any connection between those two forces. The more interesting question, Vladimir, is could it be that they are related and that somehow mass and charge have a connection, that gravity and electromagnetism have a connection? That's the more interesting question.
But does anybody know the answer?
No.
Ah.
If you did, you'd have a Nobel Prize and probably a big fat several $million grant pile in your bank account, and you'd feel pretty cool. People would invite you to parties and ask you questions about space.
Wait, but also, do we know what makes up the charge inside of an electron or a proton?
No, we'd very much like to know. We have no idea.
Oh, damn. I thought
well, okay.
Maybe like has something to do with.
No, we've learned some stuff. Okay, so I'm lying to you right now. We know some things. There's this thing called the standard model of physics. And basically, these are the kind of questions that they're asking when they smash atoms together in particle accelerators, like the Large Hadron Collider. That's what they're up to. So far, here's what, well, I can't give you the whole rundown because eventually I will start to screw this up myself. I just want to look at this whole picture here. Can I please? Oh, whoa. There we go. It turns out that protons and neutrons are made up of quarks, and quarks seem to have fractions of a charge. Like an up quark has a charge of 2/3, and a down quark has a charge of -1/3. So if you add 2 ups and 1 down, you get +1. If you add 2 downs and 1 up, you get 0. But the electron seems to have its own charge, and we don't know what the deal is with the charge inside of an electron. You got to learn more about the standard model of physics to answer questions like that. And those things will kind of come up from time to time in this class. They're all good questions, Vladimir, but they have complex answers. Instead, let's take a moment to talk about the orbits of the electrons. I'm going to erase this stuff, okay? And so I want to just say the answer to your question once again, Vladimir, is we don't know we don't know how the charge is distributed inside the electron, but we do a little bit for these two guys. Okay, let's go and return to our favorite, most basic, simple, common element, the element of hydrogen. And we'll start off with a proton. And we are going to put an electron orbiting around it. So this is a protium atom. When a planet goes around the sun, it orbits due to gravity. And gravity is a large-scale force that deals with large objects. So the planet can kind of orbit at any distance it wants from the star, provided that the solar system formed in such a way. How do I say this? This is sounding too complicated. Let's imagine that Zeus showed up in our solar system, and Zeus could grab Earth and drag it with the finger of God further away from the sun. In theory, Zeus could place the Earth at any distance he wanted from the sun, and Earth would go into a simple gravitational orbit. They would be allowed. In the world of the microscopic, the world of atoms, the electron cannot similarly orbit the proton at any old distance it wants. It's constrained to move on pre-proscribed tracks. And the place where we normally find the electron, its default orbit, is what is known as the ground state. The reason that we use a funny term like ground state is because it's going to turn out to be easier to talk about the electron orbits in terms of potential energy, rather than talking about them in terms of distance. But for the very first one, let's talk about the distance. I happen to know how far away the electron orbits from the proton. It orbits at a distance, I'm going to use an old-fashioned unit right now. 0.5 angstroms, where I've introduced a new unit called the angstrom. An angstrom is 1/10,000,000th of a meter. You guys might be more familiar at this point with nanometers. 0.5 angstroms is 0.05 nanometers. And I'll remind you guys that 1 nanometer, we use this in our homework all the time. 1 nanometer is simply a billionth of a meter. 1 times 10 to the minus 9. Both units of angstroms and units of nanometers are going to appear in our labs today, so I figured I'd throw it out there. For reasons which are a little bit complicated to get into, and they have to do with angular momentum, the electron cannot get any closer to the proton. It's moving too rapidly. Just like the Earth is moving too fast for it to get any closer to the sun, the electron's angular momentum is fixed at some low level, and it can't really get any closer to the proton than that. So it'll always at least be that far away. This is why they call it the ground state, because an electron in this orbit is kind of similar to what happens when you put your 1 kilogram test mass right on the ground. The ground is the sort of lowest point that the mass can get to. So we define that as 0 potential energy. And then as we lift the mass off the ground, it gets more and more potential energy. So rather than talk about the distances that the electron can move up to, we're instead going to talk about the other orbits it can achieve in terms of energy, rather than in terms of distance. Now, when we measure the energies of electrons, the energies in question are quite small. You guys will remember that just lifting this thing up 2 meters, that was about 20 joules, right? So these numbers are going to be way smaller. It's common to measure the energies of electrons in electron volts. You saw those in your homework last time. An electron volt is 1.6 times 10 to the minus 19 joules, okay? We define the ground state as having an energy of 0 eV because it's as close to the proton as the electron is allowed to get. Sometimes you can give energy to the electron. Usually when you slam it into another violent atom, the violent collision will sometimes give the electron some energy. And the electron can jump up to a second orbit, which is a very particular distance or a particular energy away. And we call this orbit, this is kind of like the first orbit, so we call it the first excited state. And I happen to know how much energy it takes to bring an electron from the ground state to the first excited state. The energy is 10.2 electron volts. Because hydrogen is so well mapped out, we know how much potential energy it takes the electron to go from one orbit to another. Now it gets kind of annoying to talk about the ground state, the first excited state, the second excited state. So what we do instead is we label each orbit with a quantum number. The ground state is called n equals 1. The first excited state is called n equals 2. There is a third excited state. That's n equals 3. There's even a fourth excited state, n equals 4. There's even a fifth excited state, n equals 5. You might start to wonder just how many excited states there are. Well, a lot. But it's not infinite. Before I go any further, let's just stop and think about what I've taught you here, because you've just learned something that we should probably have a discussion about. The orbits of electrons are, here's a fancy $10 word, quantized.
So they come in certain portions of energy.
I'm sorry, Vladimir?
They come in certain portions of energy because
Certain distances or certain energies. But let's
as far as I remember,
flush out, let me flush out this word quantized, and then I want to hear your comment. Quantized also means discrete. It could also mean choppy. And here's a cool way to look at it. The orbits of electrons are like pixelated. That's how I would say it. Just as the images on our computer screens are made up of zillions of little pixels, most of which are too small for the eye to see, the orbits of electrons have all these particular distances, which are very difficult to see, but are yet nonetheless quantum chunks. What were you going to say, Vladimir?
so I was just going to say that as far as I remember, like the definition of quant is the smallest amount of energy that can be like transferred or operated with.
Well, I wouldn't go that far because there are limits to how small a packet of energy that can be transferred, but we haven't got anywhere close to that level yet. We're just at the level where the electron orbits are choppy. We're not at the level where energy itself is choppy. There are different limits to those things. So you want to be careful in how you say that, buddy.
So does it have to do anything with the orbits of electrons being quantized? Does it like have a connection?
The orbits of electrons being quantized has to do with the quantization of angular momentum. You'll remember that we talked about angular momentum when I did the bicycle wheel demo.
Yeah.
It turns out that on microscopic levels, there are limits. Things have discrete units of spin. You know what? I could try to explain this. One, I'm going to do a bad job. And two, I'm going to get us further and further away from our goals. But let me just say a simple answer to your simple question. It has to do not with the quantum of energy, but the quantization of angular momentum. And from there, you can go off on your own to read about the quantization of angular momentum. Maybe I'll hint at it a few times from now. Like, for instance, why should things have discrete units of spin? I don't know. Nature's freaking weird. It's not our job to say what it should be. It's our job to investigate, right? Okay. Anyways, let's take a look at this in a slightly different way, and then I'll explain why I'm doing all this with you. If I were to try to draw the orbits by kind of drawing them out the way I've done so far, you kind of very quickly run out of space on your paper. For instance, here's a drawing of the first 3 orbits of the electron, which attempts to show you their spacing by scale. Here's the n equals 1 state, n equals 2 state, n equals 3 state. What you've learned so far is that the electron can orbit here at the ground state. That's where it kind of tends to be when the atom is cold and not bothered. If you energize the atom, you can make the electron jump up to here and it will orbit there. But the electron cannot orbit in between these two orbits. That's kind of like a no man's land. Likewise, if the electron is here, you might be able to kick it up to the n=3 state, and there it will also have a stable orbit. But it's not allowed to orbit anywhere in between. This is what we mean by the orbits being quantized. This is an allowable orbit, this is an allowable orbit, and this is allowable orbit. Rather than just keep showing you the orbits, it's cool to represent this as an energy level diagram, where each of the orbits are represented as like a rung on the ladder. And here, this is for the hydrogen atom. You can see that when the electron sits at the ground state, it has the lowest possible energy. We call that 0 eV. If you energize your electron and you can give it a boost of 10.2 electron volts, it will jump up to the next orbit and it will happily orbit there. If you can give it another boost of a few more electron volts, maybe 1.9 electron volts, you can kick it up to the third state. Give it a little bit more, you can kick it up to the fourth orbit. A little bit more, you'll kick it up to the fifth orbit. Notice that as you get higher and higher, the orbits get closer and closer together, but there's a limit. If you give your electron from the ground state more than 13.6 electron volts, boop, you kick it right off of the atom, you ionize the atom, and you kick that electron into free space where it'll go humming around like a bullet. This is known as the ionization potential of hydrogen. Okay, so the electrons can jump up, and they jump up when you energize the atom by heating it up, by smashing it into its brethren. But the electrons don't stay at these orbits forever. They tend to whip around the atom at one of these higher orbits for a short period of time, maybe 10 to the -5 seconds or so. And then after that, the electrons get tired, and they usually start to drop back down. An electron at the third orbit might, for instance, drop down to the second orbit. It might whiz around there for a little bit, and then it'll eventually drop back down. So if you leave the atom alone, eventually the electrons come crashing down. But here's the deal. Every time they drop from a high orbit to a low orbit, they lose energy. And when they lose energy, that energy must be emitted. What form does that energy take? It takes the form of a little particle of light called a photon. When the electron drops from a high orbit to a low orbit, a little wiggle of electromagnetic field comes out, and this photon is where light is formed. I wanted to show you before these physics PhET simulations. And I think I ran into the problem that I had. I was not able to do it because of the flash thing. I told you guys I was going to look into that. Of course, I totally forgot. Let's see if I can find it on their website. Maybe they've come up with a solution for that. I want light and radiation. And what I want is a radiating charge. Yeah, this is. Let's see if they'll let me just kind of run this thing right from the. Oh. Jesus. I guess they haven't really figured out the solution to this either. That's so annoying. This simulation would have been so nice to show you guys. I'm going to have to ask my coworkers how they got around this. These things were so damn cool. I would really, really love. All right. Okay, I'm not going to get sucked into that. Let's draw a little picture of what I was just describing instead. It'll have to do, I suppose. Can I erase all this, guys?
Sure.
Okay. this is how light is created. And this is the generation of a photon. We generate a photon, a single particle of light. And we're going to have another name for this. We're going to refer to it today as an emission line. And I'll explain why we call it an emission line. It's because of the way that we observe it in our laboratories. Okay, so here's the scenario. An electron drops from a high orbit to a low orbit and releases a photon, okay? So it's from high orbit to low orbit. Let's draw a picture. Here's my electron. It's going to drop, or sometimes we say cascade, from high orbit to low orbit. And a little wiggle of the electromagnetic field, a little photon, is emitted. It's a single packet of light. Actually, sometimes we draw photons like this. We want to show that they're localized, but there's still little ripples in the electromagnetic fields. We draw them like a little packet like that. A photon is like a bullet that's also a wave. It has wave-particle duality. Now, this is the high orbit. This energy is high in terms of electron volts, and this energy is lower in terms of the electron volts. And one of the rules that we discover when we study these photons is that the energy of the drop is equal to the energy of the photon. So you guys will remember that last time we had to calculate the energies of photons. Each photon has a unique energy, in fact, let's write this down. Each photon has a unique wavelength, a unique frequency, and a unique energy. They're all connected by those three formulas that we studied in our last class. The energy of the drop is equal to the energy of the photon, and let's elaborate on that. It's a change in energy, the energy from the high orbit minus the energy of the low orbit, okay? Let's, for instance, consider a particular drop. For instance, in what is called the 3-to-2 transition of hydrogen, let's calculate the energy of the drop. The change in energy is the energy of orbit 3 minus the energy of orbit 2. Let's use our cheat sheet here. Help me with the numbers, guys. What's the energy of orbit 3?
12.1.
Sorry?
12.1
EV.
EV, yeah.
How about energy number 2? The energy of orbit 2?
10.2 EV.
Okay. Can you guys subtract those for me?
So 12.
Woo!
Oh, bless
I
you.
must be allergic to math.
You shouldn't be as an astronomer.
I know, I'm just joking. I love math. I was pretending I was you guys for a second.
Wow. Wow. Throwing a punch.
What do you get for your change in energy?
1.9.
Oh.
One 1.9. Oh, never mind.
Units?
Oh, EV, electron volts.
Okay. I think the actual number is, it's actually 1.895 EV. There's a reason why I want it to a higher degree of precision. Let me just see if I got that right. Yeah, it's actually 1.895, but the number that I had there kind of rounded it up to 1.9. They only gave us 2 sig figs in the 2 or 3 sig figs in that cartoon that I showed you. Okay, do you guys have that written down? I want you to hold on to that for a second. We're going to do a little in-class exercise, very similar to the type that we're going to have to do on the test. Remember, guys, like it or not, a test is coming up, correct?
Can you put it back down again so I can finish writing it? I'm sorry.
Sure.
No, there's not. No.
Wait, the test isn't coming up?
No, right? No test.
It's just an illusion.
So it's going to be on everything that we've covered so far.
Yes, and I want to show you an example of some of the questions you're going to be asked. They're going to be similar to the homework. Let's just double check on that whole test thing. What's today? The 16th? So we
Yeah,
have next
sure.
week, and then dun dun dun. All right. I just want to remind you that these in-class exercises are going to feel a little weird, but you've got to really try to pay attention to them because they're going to come up. Okay. All right. Do you have everything, Kiana?
Yes, I got it all.
Okay. Let's talk about how we generate a unique wavelength of light, and let's calculate the 3-to-2 transition of hydrogen. Okay, so here's a really useful example problem. During the 3-to-2 transition of hydrogen, an electron loses exactly this is the energy of the drop, a change in energy of 1.895 EV. The goal is to find the wavelength, frequency, and energy of the emitted photon. Okay, let's see if we can walk our way through this. Believe it or not, class, you already have all of the skills that you need to do this. In your homework last week, you learned what formulas can be used to solve this problem. Let's see if you can find those formulas for me.
I know a few of them.
Okay, Andy, let her rip.
Just copying the rest of this down.
Sure.
All right. All right, so C equals, what is that, theta? The y, the upside down y?
It's lambda, but you can just say wavelength.
Wavelength
So
times frequency.
speed of light is wavelength times frequency. What are the other formulas?
And then E equals H times F.
Energy is Planck's constant times the frequency. And there's a third formula. We could have that too.
E equals H times C over the wavelength.
Okay. At this point, we should try to do the calculation. One, because it's practice for the test, and two, because I need this answer to go forward.
Do we need to convert to MKS units?
Oh, brilliant. Vladimir, speak louder. Say what you just said again, because that's wicked important.
I said, do we need to convert to MKS units?
Do we need to convert what?
I reckon we do. The 1.895 electron volts.
Vladimir has pointed out that this is not in MKS units, but yes, Vladimir, we are going to expect, we need to have the energy in MKS units. What are the MKS units of energy?
Joules.
Joules. So Vladimir is basically saying, we need to convert this number into joules. All right, Vladimir, I volunteer you for that task.
All right, so it's 1.895 EV times division bar. The top is joules. The bottom is EV.
Good.
The bottom on the top, you're right. 1.6 times 10 to the negative 19. And on the bottom, you write 1.
Excellent, Vladimir. I'm so glad that you figured that out right away, because everyone else, I'm not sure all of you guys would have thought to do this. That was very good on Vladimir. Okay, punch him up. Give me the answer to like 3 sig figs or more.
3, so that would be 3.032 times 10 to the 19th.
Excuse me, joules, right?
Yes.
Okay. Now what do we want to do? We have the energy in joules. Actually, guys, I've got an idea. In the interest of time, let's forget about the frequency. I just want the wavelength. So let's find the wavelength.
So we solve for wavelength, the third equation.
Okay, we have the energy, we want the wavelength, so let's solve the third equation for wavelength. How do I do that? Does anyone have the skills for that?
I can do it, but I don't know if I should.
All right, try, yeah. Give it away.
You just switch E and lambda.
Yeah. Wavelength goes up, E goes down. Today we're going to use a slightly better, I'm trying to do something a little bit extra today.
You will give us a more precise C.
C is already precise to 3 sig figs. I'm going to give you a more precise H.
Because you rounded really hard. Okay.
Is 6.63, I think. Is it 6.63 or 6.62? Why can't I remember? Come on, you stoopy. Okay, yeah, that's what I meant. 6.63. Okay. Times 10 to the negative 34. The units are joule seconds. The speed of light to 3 sig figs is 3.00 times 10 to the 8 meters per second, divided by the energy, 3.03 times 10 to the negative 19 joules. Okay, guys, punch that up for me. I wonder. Can you guys see that? I'm almost able to generate a rainbow here.
It's not completely a rainbow, but I can see the
It's
light
because I just
broken
want the
down.
intensity of light to be greater. If I bend it in just the right direction, it will be. I need a brighter directional light source. I had a very, very bright light bulb and I broke it like an idiot while doing a demo.
Wait, I have a quick question.
Yes.
So you said that electrons can get energy by clashing with other atoms or by heating the atoms up, right?
Yes.
So, but can photons transfer energy to the electrons?
Yes. There's only two ways. You can smash it into another electron or you can zap it with a photon. That's correct. Both are correct.
So, because I have a certain understanding how the color occurs, but not completely.
Wait, can you say that one more time?
I have some kind of understanding of how light, of how color comes into existence, but not like completely.
Well, that's where I'm going with this. But
Oh,
first,
okay.
I need you guys to give me an answer.
Oh, I have it.
All right, what is it?
6.56 to the times 10 to the negative 7.
Units?
Meters.
Okay. I have a test for you guys to see if you can do this without me. This is good. Can you guys each in your own personal hell, I want you to each do a test and see if you can convert that number to nanometers without my help. See if you can do dimensional analysis on your own, because I'm looking for a light bulb right now so I can do a cool demo to make this class more fun. So while I'm looking for my light bulb, see if you can convert that using your own powers. I have this light bulb right here. What the hey is going on? Guys, I'm so confused. Every time I try to clean, I regret it. pray to the gods that this works. This will be powerful enough.
Is that a lens?
No, it's just a big ass spotlight that is much brighter than this piece of shit IKEA lamp that I'm holding here. I'm just trying to get a really bright light source so I can blow your socks off. Where am I going to plug it, though, is the question. All right, here we go. I need to get it closer, though. Okay, what'd you guys get? Did anyone, how many of you got an answer? Show me your hands. How many of you got a number of nanometers? I only see one hand. That's pissing me the F off. I thought I taught you guys dimensional analysis. 2. That's it? Mariah and Vladimir are the only one. Nick, what do you got? Taryn, what's going on with you?
I'm still punching over here.
Talk to me, Taryn. Talk to me, Mia. I care about you guys too, you know.
I know, I'm still punching it in. I'm sorry.
Did you set it up with the numbers and the units?
Yeah, I did.
Okay, well then punch it. Just punch it. It shouldn't take forever. Taryn, why don't you tell me what you got so I can check your moves? I gotta keep track of you. Come on, baby. You can do this. I've been trying to get this right for the last 3 semesters and I've been failing. But you guys take so long to do your calculations, it gives me a chance to experiment. You've got to get the angle. See, you usually have to collimate the beam. You have to make it into a pretty narrow beam, but this is already kind of collimated. I can see it. Can you guys see it on the camera? It's starting to show up.
Yeah, I can see it. I could see it even with the previous slide as well. It's more pronounced now, though.
At school, I had a projector that had a 410 watt bulb, and it was really monodirectional. So it was I got really good at doing it, but I'm still not that good at doing this from home. I've been trying every semester and kind of failing to get the rainbow.
So would it be like, if it comes out well, is it like a really well-defined rainbow?
Oh yeah, it's a beautiful rainbow. It looks awesome. It's part of what we're about to do here. So what did you, all right, Taryn, what did you get? You should be done punching by now, right?
It's definitely super wrong.
Well, do you know what the right answer is?
No.
Then how do you know what the wrong answer is? Everyone says they know an answer is wrong, but they don't know what the right answer is. What'd you get?
I got this really weird number. It was like 3.179.
Nick, you did it wrong.
I'm using it wrong.
And you did it wrong too, Taryn. Okay, Taryn, you're going to have to work with me then, okay? So work with me. What's your first step in dimensional analysis?
So you get, well, after setting it up, or?
I'm talking about setting it up. Setting it up is a multi-stage process.
Okay, so the units go first.
Okay, fine. But first you have to make a division bar, right?
Okay, yes.
Okay. Units go first. So tell me what the units are.
So on the bottom, it's going to be the M for meters, and then on the top, it's going to be NM for nanometers.
Okay, and what's the conversion factor?
I believe the nanometer is 1,000.
No,
I
why don't
think.
you just look it up? It's in your notes. I gave it to you like, remember 5 minutes ago when I had an atom with the electron? I wrote it down right there for you.
Yes. 1 nanometer equals 1 to times 10 to the negative 9th meter. So
All right, now let's transition over to, oh yeah, okay, keep going, Taryn, keep going.
On the top it's 1,
Yep.
and then on the bottom it's 1 times 10 to the negative 9th.
Nick, if you look what you did, you'll see that you got those backwards. You screwed.
I 100% got those backwards.
All right.
I
Don't.
had the right idea, just did not execute.
Yep. Okay, now punch them up. Take that and divide by that. What do you get? Just read it to me, Mia.
I got 656
Units?
nanometers.
Okay. Let's find out what color that is. So it turns out that wavelength is deeply related to color when it comes to light. And that's part of the story that I have yet to tell you guys. Did everyone else get 656? Now look, you all took a moment to try to solve this and convert it on your own. If you didn't get it, you should be having a talk with me. We should figure out what's going wrong and we should fix it, okay? Because remember, you'll have to do this independently on the test. So this is a good practice.
I think personally, I get the, I can calculate everything correctly, but as far as the conversions, I think that will get me confused.
Sabrina, that confuses me because I think of them as the same thing. The
Okay.
conversion is the calculus. I guess.
I mean, like the numbers, the translation, for instance, like just now you gave us the 1 nanometer. So I have to make sure I have all those factors before, you know what I'm saying?
Right. And well, they're in your notes, but let
Okay.
me give you a hint about this. When it comes time for the test, I'm going to give you guys a formula sheet. And that formula sheet will have all of those conversions in an easy to locate place. You'll also have them in your notes, which you could use.
Yeah.
So like, in theory, you shouldn't even need the formula sheet, but let me just show you what it's going to look like here. The second page of the test after the cover sheet will look like this. And it's going to have all the formulas you need in a compact place. And it will also have all your conversions. Notice 1 nanometer is a billionth of a meter would be right there.
Okay.
But don't get cocky and think this is going to be easy because you still have to know what the units are for all of these things. Like Vladimir is pretty good. He knew right off the bat, if we're going to be plugging into energy here, we're going to need to have joules. But I suspect not everybody in this class would have thought to do that. I would like you all to think to do that, but I have to figure out how to convince you that it's important, okay? Convincing you is not so easy. So if you're saying I can do dimensional analysis, but I don't know what the conversions are, then my retort to you, Sabrina, is I'm going to provide them all for you. Again, I've already provided them in your notes, but I understand they can be hard to find. So they'll be right there. Does that make sense?
Mm-hmm.
In fact, I ought to send that to the whole class so they can start practicing. That's something I should do at the end of class today. Okay. The question is, what type of light has a wavelength of 656 nanometers? Believe it or not, the first person who ever did experiments in optics was none other than Sir Isaac Newton. And he did the experiments that I was lamely trying to do above, where I was trying to generate a rainbow with a very bright light source. A white light source contains a whole bunch of different colors. And if you pass it through a prism, you can get the prism to disperse the light and separate it into its component wavelengths. Now, I was just getting the little bit of a shadow of a rainbow here, probably because so little light is going to leak out of my prism. Or you can actually, all right, wait a minute. Let's see if you guys can see this. Without the light dimming it, if you get the angle just right, the trick is how to get the rainbow without washing it out with the rest of the light.
I can see it.
Yeah.
To the right of my, like
It's not the most
I've seen it.
rainbow I've ever made. What I want to do is do it this way to keep the light off of the camera. There.
Yep, I see it right there. Yeah.
And
Yep,
you can
perfect.
see that kind of red and orange are on the left, and then there's
Mhm.
yellow and then blue and then kind of purple. When the light source is brighter, it's even easier to see. I'm trying to make the intensity of the rainbow brighter. This is one of the best I've ever gotten, and I'm still not satisfied with it, but okay. Let me show you a cartoon of what he did, and let me turn this light off because it's heating the shit out of my apartment, making me hot. Okay. The way you can avoid that crappy experiment that I just had is you have to collimate the beam. So what you want to do is you want to take that light source and you basically want to restrict it so that only a narrow beam of light comes out. Let me show you a cartoon version. So rather than just letting the photons scatter everywhere, you kind of take like a cardboard box and put a slot into it. I have tried this, but it didn't work because it still wasn't enough light. You collimate the light into a pencil-thin beam, and when the beam strikes the glass, the component wavelengths all separate. And what you get is a rainbow called the continuous visible spectrum. Isaac Newton was the first person to make this rainbow. And it took him a while, but he figured out that basically the white light was comprised of all these different colors. He discovered that he could take the rainbow and he could push the rainbow onto the glass and form it back into a white beam of light. So he argued that the beam of light was being separated into all these different colors. Eventually, through experiments in optics, people discovered that they could peg a wavelength to each color. Your eyes are sensitive to light that goes from 400 nanometers, which is purple, up to 700 nanometers, which is red. And all the other different colors that you're familiar with perceptually are different wavelengths. The order of the colors is always the same. If you go in reverse order, it goes red, orange, yellow, green. This color is what Newton called blue, the sort of sky blue. In Newton's day, dark blue was not called dark blue, it was called indigo. And then, of course, violet at the end. And if you read this backwards, because depending on if you flip the prism up or down, you can actually get the red to come first. Actually, you guys saw that on my screen. When I was doing it, could you see that red was on the left and that purple was on the right-hand side? If you flip the prism upside down, you can put purple on the left. So if you spell it backwards, it's spelled Roy G. Biv. That's the acronym that people use. I actually prefer VibGyor, which no one uses except for me. But VibGyor is better because then short wavelengths are on the left and red wavelengths are on the right. And this is called the visible continuous spectrum. Let's try to leave our result from before up, but let's take just a couple of quick notes up here.
So does this spectrum contain all the colors possible in the universe?
No, it's only the colors that your eyes are sensitive to. We'll get to that in just a second. That's a good question, Vladimir. But right now we're talking about a narrow range of light, only the range that, see, your eyes can't see infrared and radio waves. So I should start by talking about something that you can see, because seeing is believing. And then I'm going to stretch your minds past that point.
Seeing is believing.
So let's just take some notes on what I've tried to teach you just now.
I have a quick question.
Yes, ask.
So, you know how like you just showed us that like the lower number is like violet and the higher number is red? But
Yes,
why? Yeah, so if it's like that, then why does a rainbow start with red and end with purple and not like flipped over?
I just tried to explain the reason why, Kiana, but it has to do with the angle at which you're seeing the droplets. I see what you're saying.
Yeah, because I'm still a little confused on that.
Okay, watch. Let me try to demonstrate. In this configuration, when I make a rainbow, can I do this again? can do it, but can I make it bright enough to please you? Wow, how did I get this so good before? Okay. This isn't the best rainbow I've ever made, but what color is red on and what color is blue on?
Red looks like it's on the left and
Good.
blue on the right.
If I go in the other direction,
Can't see it.
I'm trying to do this while seeing what you guys can see, because the camera can you can almost
I
see
see
it.
it. So
Yeah,
Oh,
I can
yeah,
kinda
yeah,
see it,
now,
yeah.
yeah.
What color is red on now? What color?
The right
On the
side.
right. Yeah, on the
So
right.
you see, it has to do with what angle. When the light hits the prism and goes like this, red is on the right. When the light hits the prism like this and goes to the right, then red is on the left. Did you see that, Kiana?
Yeah, that makes sense. I'm just like,
So,
I don't know, maybe it's
so-
just because the distance I'm always in the position.
No, but it's because when you see a rainbow, you're always on the ground, right?
Yeah.
The sun is up here, and
Mhm.
it's hitting some droplets of water which are scattering down to your eyes. In
Mhm.
fact, if you think about it, Kiana, in a rainbow, because of that, because the water droplets are everywhere, the red ends up being both on the right and on the left, right?
Oh yeah, I've heard
You see what I
of a
mean?
double rainbow, actually.
Hold on, wait. I'm trying to make a point that was similar to what the demo I just did was.
Oh, never
Kiana,
mind.
the sun is up here somewhere, right? And it's shining
Yes.
low. And here's some droplets. When it hits the droplets like so, it's like me pointing in one direction, so you get red on the right, correct? And when the sunlight hits the droplets,
Oh,
now you get red on the left, and it makes a ring.
I
You
see. Yeah, I get it.
So it's the same thing. It's just that you've got a million different prisms all in the form of water droplets.
Yeah.
Atmosphere.
So the rainbow is actually circle.
If you get enough droplets and enough scattering, sometimes you only see part of the rainbow and then the angle isn't right or there isn't enough water droplets there to do it.
So then how does a double rainbow happen?
That's that's probably because that's a great question. It's probably because there's like different pockets of water droplets. Like here, there's the sun and there's some water droplets over here, but you might actually get some water droplets over there and the geometry of it comes out just right. You need to have the water droplets at the right height. The rainbows are scattering everywhere, but you need the rainbow to scatter towards where you're standing, you know?
Yeah. That makes sense.
Yeah, something like that. But let's not miss the big picture here, okay? Hold on, first let me unplug this. But that was cool. I actually managed to answer your question, which is always exciting. Okay, so Newton, what he did is he took white light and passed it through a prism. When you do this, we have a very special word for it. We call it dispersion. That's the fancy $10 word. When you break apart light into its component wavelengths, it's called dispersion, or sometimes it's called taking a spectrum. And he created something called the visible continuous spectrum. And the visible continuous spectrum, let's draw it out the way we had before, goes violet, indigo, blue, green. Let's see if any of these markers are good. Yellow, orange. They don't really make yellow dry erase markers. And then red. Now, I don't know if Newton actually pegged the wavelengths to it in his day. This is about as far as he got. I think it's important for you guys to know that red has a wavelength of 700 nanometers. Violet has a wavelength of 400 nanometers. I want you to memorize this. And somewhere in the middle of the visible spectrum, green is about 500 nanometers. And this is called the visible continuous spectrum. It's the wavelengths of light that you guys are sensitive to. So one of the first things that I'm just telling you here that I hope you're taking the right takeaway from, color is equal to wavelength. Wavelength and color are the same thing. But because we can peg wavelength to frequency and energy, you can also relate color not only to frequency, not only to wavelength, but also to frequency and energy, which is kind of interesting. There's a unique energy for purple photons that is different from the energy of red photons. In general, the mnemonic device people use is to take the rainbow from the other direction. They sometimes call it Roy G. Biv, is the nickname that engineers use. Like I said, I like Vib G. York because I like to have the short wavelengths on the left, but to each their own. Now, guys, we computed that when a hydrogen atom has an electron that drops from orbit 3 to orbit 2, it will release a unique photon of 656 nanometers. Let me show you the visible spectrum again. What color is 656 nanometers on the visible spectrum?
Must be greenish,
Red, orange.
yellow.
It's like a
Definitely not green, definitely
like-
not orange.
burgundy, reddish.
Red.
I'd say it's pretty darn red. I mean, look,
Oh,
this
it's
is
6. Oh my god, I thought it's 556. It's 656.
656. That's okay. So 656, let's see, 60, 70, 80. Yeah. So 652 would be right here. I don't know about you guys, but that looks pretty darn red to me, doesn't it?
Mm-hmm.
Yeah, it does.
Yeah.
Okay. So what we have learned is if a hydrogen atom, let's go back to our hydrogen atom for a second. If I have a hydrogen atom and I have an electron that drops from orbit 3, oops, I need a different color, from orbit 3 down to orbit 2, it will release a unique photon, which is a pure red photon with a wavelength of 656 nanometers. This is the emission line or the 3 to 2 transition of hydrogen. Now, why would I be telling you about this photon, 656 nanometers? It's one of the most famous photons in all of astronomy. Let me show you where you might find it. Let's take a trip out to outer space once again, but this time let's go to the Rosette Nebula. Somewhere in outer space, there's a newborn cluster of bright, bright stars surrounded by a pocket of hydrogen gas. Astronomy picture of the day. Yeah, this is the one I like. And as those bright blue stars in the center of the cluster heat up the surrounding hydrogen gas, as Vladimir hinted earlier, you can use photons, you can use light to energize atoms. And all of the hydrogen that you see here is all getting energized with all of the electrons jumping up to the third orbit. Then, as the electrons drop from orbit 3 down to orbit 2, all of the hydrogen atoms start emitting a pure red light at exactly 656 nanometers. All of this cool red light that you see here in the Rosette Nebula all comes from the 3 to 2 transition of hydrogen. And because this is an emission line, they refer to these types of nebulae as emission nebulae. This nebula is getting powered by the microscopic engine of electrons jumping around inside of atoms, of hydrogen atoms. Now, it turns out that the 3 to 2 transition is not the only transition that hydrogen can do. But you guys will notice that it took a few minutes just to calculate that wavelength because we're kind of slow at this stage in our development. Let me show you a kind of chart that shows you some of the other transitions that hydrogen can do and see if you can make a wild kind of sense out of all of this. This chart here shows you the energy level diagram, showing you both the transitions of the electrons and the emission lines that hydrogen can produce. For instance, up to now, we talked about the 3 to 2 transition. And you guys will notice here that when an electron drops from orbit 3 down to orbit 2, it will produce a photon at 656 nanometers. This has a special name in astronomy. This is known as hydrogen alpha, and it is the most famous of all emission lines. An emission line is when an atom produces a very pure type of light. An emission line. Okay, let's have you guys try it. Hydrogen can also produce another emission line. Hydrogen beta occurs at 486 nanometers and is a teal blue line. What transition is responsible for the hydrogen beta line at 486 nanometers?
Is it the from 2 to 1? Is it that one?
Not from 2 to 1. 2 to 1
Oh wait, oh gosh.
produces
Oh,
120.
it's from 4 to 2.
There you go. So when the electron drops from orbit 4 down to orbit 2, then it will produce hydrogen beta, which is a blue-green 486 nanometer line. This one is another famous line. It's called hydrogen gamma. It's a purple line at 434 nanometers. What transition produces the what transition produces the hydrogen gamma line?
5 to 2.
5 to 2.
So
Good.
the bigger the jump, the more energy is being released.
That's right.
Actually, that makes sense, of course.
Energy,
I guess I see it in the image too that you just shown us, like, because I realized that like toward the middle, it was more of a turquoise color versus outside of that. So I can definitely see the
you mean this line here is turquoise?
no, the image that you just showed us with the stars in space.
We have to be careful there. Some of these colors are due to emission and some of them are not.
Okay.
For instance, I don't
Okay.
know how to explain this. It's interesting that we see so much hydrogen alpha, but we don't see the blue or the purple line. The blue that you see here surrounding these stars is actually due to something totally different. And I will eventually tell you about that, okay? There's a lot of complicated things going on here, Sabrina. I'm giving you your first little taste of unlocking the secrets, but you haven't unlocked all of them yet. So just focus on the red for now, and we'll talk about the other colors later. I am feeling sneezy. How am I doing on time? Anyways, I'm losing track of this. Oh my gosh. Am I 15 minutes over? What the shit? Why didn't you guys tell me? I'm so sorry.
I was
I was
enjoying
starting to get intrigued, so that's why.
I know. Okay. All right. So we were actually having fun. All right. I am deeply apologize. Let me say this. We didn't quite, I went a little slower than I wanted to today. I don't know what happened, but here's what we're going to do in our labs today. In our labs, we're going to be studying the emission lines that all kinds of different atoms produce. And so I'm going to show you a bunch of, so we're going to keep talking about this, Sabrina, and I'm actually going to show you the real deal stuff. What we're going to do in our labs today is I'm going to show you a bunch of different atoms, and each atom is going to produce a different set of emission lines, and we're going to actually color them in. Now, I forgot to mention this, and shame on me, but you know what would be really helpful for this lab today, guys? I should have warned you about this, but if you have a set of colored pencils, I bought this at Job Lot for $7 at the beginning of the semester. I should have warned you guys about this. Do you guys have like crayons or colored markers or something? Anything? You don't need all the colors.
I had a pack of colored pencils right on my table.
Oh, perfect. If you don't have colored pencils, one thing that you might be able to do that might be tricky is you might be able to to take the sheet. Where's the sheet there? And you might be able to like use MS Paint or something to draw in the lines like this digitally.
Actually, I have a question about that.
Yeah, okay.
I don't have a printer at home, so usually we do some of the worksheets like that. I just use my iPad. For this, can I still use my iPad, or would you prefer if I like wrote it down on a sheet of paper?
I don't mind if you can use your iPad, but can you use some coloring tool so that you can make the
Yes,
lines
I can.
appropriate colors? Okay.
Yeah.
And that sounds great, Kiana. Okay.
Okay, I just wanted to make sure.
Sure. Guys, I am so sorry I went over. I think I got caught up in it too, and I didn't realize what was going on there. Let's stop. Let's take a little tea break. Jesus Christ, I can't believe I did this. All right, so it's 1:48. Our lab today isn't too long. I'm just going to show you a few elements, and we're going to draw some cool lines. So why don't we start at 2 o'clock, okay, to make up for our badness. So
Are
at
you
2 o'clock.
busy? Are you busy after the lab?
No, if you want to chat about stuff, I'm down to do that.
All right.
Okay. All right, so let me take a little tea break, and at 2 o'clock, we'll get back to it. Okay, friends, welcome back to Lab 5. We're going to do a very special lab called Spectroscopy. I would have liked for us to have more time to talk about elements and the type of emission lines they produce, but maybe we'll just kind of jump into learning about it intuitively, and then we can try to understand more about this on Thursday. So what are we going to do? First, we're going to need that sheet or something like it. This is a set of spectrograms. Spectrograms are we're going to plot the type of photons that we see being emitted from different types of elements. You'll notice that our spectrogram here today, it uses a different set of units than nanometers. It uses angstroms. So instead of having 400 nanometers on the left and 700 nanometers on the right, it has 4,000 angstroms on the left and 7,000 angstroms on the right. That's fine. We're going to be able to convert from nanometers to angstroms just by adding a 0. In the old days, when people did spectroscopy, when they analyzed the emission lines from different substances, they actually tended to use a prism, just like Isaac Newton did. But over time, we discovered that there were other things that could also break apart light into its component wavelengths. One that's used all the time by professional astronomers is something called a diffraction grating. And a diffraction grating is a thin film with these kind of long molecular strands in it, which just like a prism can disperse light, but unlike a prism is a thin piece of paper. For instance, here, let's just do a quick demo. Here's a lighter. Let's hold the diffraction grating up to the lens, and then let's light the lighter. And you guys can see that I can produce some rainbows. I can separate that white light into rainbows just using this diffraction grating. Now, this diffraction grating is circular, so the different spectrums kind of shoot off in all directions. If you design your grating in a clever way, you can get the diffraction grating to scatter one spectrum in one direction. And that's sort of what this device does. This is called a spectrometer. A spectrometer's job is to break light apart into its component wavelengths so that you can analyze those wavelengths and see what kind of elements is producing the light. There's a piece of film in here with a very thin slit. This tube is where the light enters, and the light travels down this tube and it strikes the diffraction grating, which you can see there. The diffraction grating is what's going to work like a prism. And the diffraction grating is going to scatter the light over to here and project it onto a film where numbers have been printed. Unfortunately, these numbers will be in nanometers. Now, I'm going to use my iPhone for this, but let's see if I can hold this up to your camera. You guys can see in there. Let me see if I can illuminate it with some lighter light. You guys can see that the numbers at the bottom are the wavelengths in nanometers, right? You've got 700 on the left, and you've got 400. Let's see if I can do that. How did I do that? 400 on the right. Oh, there we go. Okay, there's 400, right? In our spectroscopes, things are going to be backwards, so we have to be careful here. Here I have 400 on my left and 700 on my right. But in the spectroscope, it's all reversed. Okay, we're just going to have to be careful of that. Okay, let's talk about the elements and such that we'd like to analyze. And let's switch over to my iPhone and see if I can pull this off. I have done this before with my iPhone 5. I've never done this with my iPhone 7. So try to go easy on me, guys. We'll see what we can do. Obviously, this lab is way cooler to do in person, but it's such a critical lab. We have to do what we can here. So I'm going to share screen to my iPhone.
So this is lab number 5.
Yeah, I'll set that up in a second. Okay, here we go. I just had that pencil here. Okay, so let's put our names down. As Vladimir reminds us, this is lab number 5. Always good to keep track of that. For submission purposes, we are AS1020. And be a good student and put your section down, whatever it is. One of those, choose one of the 3, whichever one applies to you. Okay, we're going to analyze a few particular gases. I'm going to try to hold this steady. So under gas name, our first gas will be hydrogen. Our second gas will be helium. I don't know if we're going to do all of these, but I'm going to write down an ambitious number, but we might do a smaller number because it takes a while just to pull this off. It depends how quickly I can look at them. Mercury, neon. I'd like to do neon. And then I'd like to do an incandescent bulb. That's a bulb with a filament. I'd also like to try to do the solar spectrum. I don't know if we're going to do all of these, but okay, so you guys should already have a guess about what the hydrogen spectrum will look like. From our lecture today, what should hydrogen look like?
Pure red. If it's or I don't remember the exact name. It's like bluish or violet.
There were 3 lines. There was a red, a blue, and a violet, right?
Yeah.
You will discover that these guys have their own unique spectrum. Let's see if we can pull this off. Over here, I have a, let's see if I can twist this a little bit sideways. So this is a power supply where I'm going to place gases of different materials and heat them up. So let's roll over here, my rolly chair. I don't know if I put these away right, but this is supposed to be hydrogen.
This feels very familiar.
You may have done this
in chemistry class.
Okay, this hydrogen I remember kind of sucks, but we're going to try it anyways. Hey guys, what color do you think you should get? Like, let's think about this. You believe that this is going to produce a red, a blue, and a purple line. But before I break them apart with my prism, this tube contains hydrogen gas, and I'm going to heat it up by sending a current of electricity through it.
Will be a composition?
Huh?
It will be a composition of all 3?
That's right, because before we separate them into the component lines, all 3 lines will be present and they'll be overlapped into one beam. So Vladimir, let's use color theory. Red plus blue gives us...
wow, violet.
Right, and then violet plus violet will give us...
Violet as well.
I have to plug it in first. Hold on. Arrgh. Getting too old for this shit. All right, hold on. All right. Oops. Okay. Sure enough, it glows with a violet light. And that's the composition of all three of those lines. Now what we're going to attempt to do is, even though I gave you the values in today's lecture, we will experimentally determine them using our spectroscope. Let's do a test and make sure that this camera can actually look in and see this thing, see if it focuses. Okay. So what I want to do here is, unfortunately, it would be really great if I was an octopus, because this requires sort of one more hand than I have available.
You have to be a Zaphod Beeblebrox.
I really need to be Zaphod Beeblebrox right now. That is correct. But that doesn't look too bad. Let's see if I can. Okay. I'm going to open up these blinds because it helps to have a little bit of background light too. The background light will illuminate the spectrogram. Okay. Are we ready to start looking? Let's see if we can do this, guys, okay? What is the wavelength of the red line?
Right in the middle, it's kind of like
650.
650, and a little bit more.
How about the blue line?
6.
Like
Um,
4.
5, 6, 7, 8,
Oh,
85, I'd say.
85.
85.
Now the purple, look, can you see how it's already starting to poop out? This thing really sucks. The others aren't as bad. To get the violet is going to be really, really hard for us. Well, let's see if we can get it. Is that me or you? That's me. No, that's not me. I don't use that tone. Okay. Let's turn off for a second. Let's focus on getting those two down, and let's give that bulb a chance to just to catch up. Okay, so I need a couple of different colors here. Let's see. So I can't really. Blue. That's a nice teal for hydrogen. There's a good violet. Let's take out a whole Roy G. Biv. Sooner or later, I'm going to want them. Nice to have green in there somewhere.
So it's not exactly blue. You said it's teal.
Well, you saw it yourself. Didn't it look kind of sky blue? It
Yeah.
looks kind of sky blue to me. People sometimes call it teal, but to me, it looks very sky blue. That's how it looked to me. You guys can tell me what you think. Okay, so let's go to hydrogen. You guys said 650 for the red line, right? So this is 6,200, 6,400, and 650 would be a red emission line right there. Okay. Now let's do the blue line. The blue line, what did you say it was at, Vladimir? Do you remember? It was like 480 something?
Yeah, I'd say 485.
So 4,200, 4,400, 4,600, 4,800.
Can you go to the left a little bit with the camera? Oh, so it like that. Okay. 2 dots. All right, got it. Thanks.
Now we know there should be a purple, but hydrogen's, you know, when I had to grab everything from the lab when COVID hit, I knew that there was one hydrogen which was burned out, and I knew that there was one hydrogen which was good, but I was in so much of a rush to get out of the building that I grabbed the wrong hydrogen. So that's why I'm still struggling with this shit hydrogen here. Let's see if we can get that purple. If not, we'll fake it. Wow. It's totally zapped, guys. Look at it. Look how faint it is.
Pretty
Okay.
weak, yeah.
I'm sorry, my hydrogen is damaged. Otherwise, we would be able to, I've done it before, but I really have to go and get that other hydrogen. Can we just cheat? The other one is at like 430. It's if the hydrogen had more, you know, because hydrogen is so volatile, I think it leaks out and then it's hard to like, to heat it up. So let's just cheat and let's put the violet one where we know it should go at 430. That kind of sucks, but hydrogen's so important. I want all 3 lines. Do yourself a favor because I'm going to refer to these very often in our class. This is hydrogen alpha. This is hydrogen beta. And this is hydrogen gamma. I want to be able to refer to those. And I want you guys to know their nicknames, okay? This is the most famous spectrum in all of astronomy. What we're doing right now is called spectroscopy. And it's kind of a big effing deal because all of science proceeds by analyzing light in this way. It's not just astronomers that do this. Okay, hopefully helium won't give us as much of a difficult time. So let's try that out. Now these get quite hot. So hold on, guys. I got to go grab an oven mitt, okay?
So what was the second one? The first one was 650.
650. Can you see that?
A little bit. Yeah. Yeah. So it's closer to 5,000. All right.
Are you all set with hydrogen, folks?
Hydrogen alpha, gamma, and beta.
Hydrogen alpha is red. Hydrogen beta is blue. Hydrogen gamma is purple. All right. Now y'all going to be helping me here, right? Let me twist this around. You're going to help me measure the wavelengths. That's your job. I need your help. So here's helium. Notice it's a totally different color than hydrogen. I'm going to zoom in a little bit to maybe 1.6 or 1.8. Okay. All right, we're going to do these lines one at a time now. Let's get the spectrum first. Hold on, let me focus. Okay, let's start left to right. What color would you say that first line is? Paul, let me zoom in a bit. Let me see if I can zoom in here. Ooh, do you see those red lines?
Yep, I see them.
What wavelengths are the 2 red lines at?
I'd say
700.
700 and what else?
And then 740.
No, Sabrina.
No, it's like 660.
600 is on the right, Sabrina. Do you see that?
It's like 660.
660. Okay, let's start with those 2.
So on top I saw decimal numbers. Does that measure energy in electron volts?
Very good, Vladimir. That's right. Those are the energies in electron volts. In fact, you can see, Vladimir, you'll notice the numbers run from about 2 to 7. One of the reasons electron volts are such good energies is because the visible spectrum is around 2 to 7 electron volts, and those are cute numbers, right? Okay, so 700 was one of our red emission lines. This is helium, right? You also said, Sabrina, did you understand why it was 650 and not 740? Or did that confuse you, Sabrina?
I had just seen a, so maybe I was reading it backwards. I don't know.
Yeah, Sabrina, let me explain what was going on so you know the next time you look, okay? What was happening there is 700 on the spectrogram was here. 1, 2, 3, 4, 5, 1, 2, 3, 4. But what you didn't realize is that 600 was over here in the spectroscope. So when you saw your line here,
Yep, I see those ones.
you were counting it as 7, 10, 20, 30, 40, but you were not realizing that it was 600, 10, 20, 30, 40, 50, 60. Do you see what I mean?
Okay, yep. Okay. All right.
Unfortunately, the spectroscope is reversed from the spectrogram. So that's what makes this confusing. All right, so this was 620, 640, 660 was the other red line. Let's see if we can get that next line. 2.5 seemed to be pretty good magnification. Okay. All right, so what color would you say that middle line is?
Looks pretty orange.
And what's its wavelength?
590.
Maybe like 580.
Honestly, it kind of looks like 585.
Yeah, I would
Yeah.
agree.
585. And that color is really interesting. I love doing this in the lab because sometimes people say it's orange, sometimes people say it's yellow. It's kind
Looks
of
like it's in between.
yeah, it's like a goldenrod color. It's really beguiling. I stare at it, and sometimes I'll just stare at that line and be. One of the cool things about spectroscopy is just the pleasure of colors. And I'll stare at that line, and it's so deep and electric, and I'll be like, "What fucking color is that?" Anyways, I think it's kind of like a goldenrod. I wonder if I could get such a thing, or maybe I could make such a thing. I've got a lot of crayons here, but I'm. Oh, here we go. Here's kind of a goldenrod. Look at that. Look at this. This is kind of.
Okay.
It's kind of somewhere between orange and yellow. Like, look, here's yellow, here's orange. Wait.
That looks like a good in between.
Yeah, good enough, right? So, and that was at 585, y'all said, right?
Mm-hmm.
So 520, 540, 560, 580, and just a little bit past is
What is
585.
16?
All right, let's see if we can get some of those others. Go up to 2.5. I'm really grateful for this phone that Joel last semester gave me. It's really good.
Oh,
It's okay. I don't mind the noise. It's no big deal. Okay. Looks like we got a couple of greens, guys. Help me out with them greens.
I can't see it. Oh, one of them looks like it's on 500 exactly.
Correct?
500, maybe 520, I'm assuming.
60, 70, 80. I'd say 590 even.
For that second one, yeah.
The big ticks are 10. The little ticks are 5. Right? Sorry, it's not easy to do this, guys. I don't know, 590, 580, something like that.
Actually, that green looks a little bit more like blue than it does like green. I don't know if that's just me.
No,
But
if you go past 500 is where it is still kind of teal.
yeah, exactly. It's like a teal
I don't wanna-
cyany
I think
color.
There might be a blue line, so I'm gonna hold on. I'm just, rather than fish around for all the crayons, just so we can get through this. 500, you're right, it is a little bit teal, so here's what I'll do. The one at 590, I'll start with a green, and then I'm just going to give it a little teal treatment here. Oh. Someone's blowing me up. That can totally wait. Okay, let's see what else is there. There might have been something else. 2.5.
So the second was really close to 500.
It was like 590.
590.
Can you see it? I mean, what do you?
Maybe more like 490.
Oh, yes. Sorry. That's what I meant to say. Sorry.
Yeah, I can see this. Oh yeah, I can see it brightly now. Yeah.
So, looks like we've got one kind of blue line.
It
in
says
one
470.
So, Professor.
Yep.
So I don't know. I hope you will accept this because mine is pretty crude. The reason being the absence of a printer, so I had to do it by hand.
That's fine. I mean,
But I did my best job.
Vladimir, I'd like to think you have the skills to reproduce a bunch of black lines on a paper.
I mean, yeah, but they're not as precise. I tried to do. I have a ruler, but they still look kind of crude.
If you use, you know how I would have done it, homie. Let's say I was you, okay? What I would have done is I would have taken a ruler, and since they're divisions by 10.
Oh yeah, I did that. I did that.
I would have gone like, okay.
It's like
Like
by
that.
5 millimeters.
Yeah, dude, I'm sure you can figure it out. Impress me with your skills, okay? Okay, now there was a blue and there was a violet line for helium. The bluish line, it was kind of a darker indigo. Let's see if we can fish an indigo out of here. Come on, baby.
It makes so much sense to give a different name to a dark blue than just say it's
Right.
dark.
Why, yeah, why blue and dark blue? That's so unimaginative, right? Okay, so there was kind of a darker blue.
No, I'm pretty sure other languages have like legit a different name for dark blue.
Perhaps. Maybe they, well, yeah. Okay, so the first one, someone said 470. So 420, 440, 460, 470 would be here. And then there was a darker indigo. It was close to 450. And I think that's our spectrum for helium. Notice the visible spectrum for helium is a lot more complex than hydrogen. Why is that? It's because helium has 2 electrons racing around the atom. And the 2 electrons have more jumps that they can make. Let's move on to Mercury. This is where I try not to burn myself.
I'm missing one of the other violet lines. Can you go back to the helium real fast? Two. Okay.
I'm just going to try to deal with this bulb while you fiddle with that.
So while you're doing that, the 2 blues was a dark blue and a light blue.
Yeah, one was kind of like a, one was like a sort of a sky. You know what? One looked kind of indigo and one looked really violet, but it might have been part of the CCD. I decided to make the one at 470 like a light blue.
Okay.
And I decided to make the one at 450, just before 450, such a dark blue that it was really more of an indigo.
Okay.
What's our next one? Mercury?
Yes.
How are we doing on timer? I think we're doing okay. I'd like to finish by 3 if possible. I think we're doing all right. Let's throw Mercury in there. Why not? It's always cooler if you can get a few extras. Notice that Mercury, totally different color than helium. And it's even more blue than, you know, the hydrogen is quite purple.
I can actually see some purple, like
Yeah,
right before you
purple
just
in the
wheeled
middle.
in. Yeah, right in the middle, I can see it.
Yeah, I'm wondering about that. There's something happening. The gas has a different density there than it does there, and the voltage probably changes across this thing. So it might be the way that it's exciting the gas. There's some interesting physics going on there. Let's take a peeksy-weeksy at what we got. All right, this is a little difficult to hold it all, so bear with me. The angle has to be just right to see it.
There's a lot of colors.
Mm-hmm. Notice the more complex the atom is, the more crazy the spectrum gets. Oh my God, that's a lot of lines. Let's not do anything past 700 because those are hard to see for your naked eye. This camera in some ways is more sensitive than the naked eye.
I'm using a very limited selection of very poor quality colored pencils. So I'm trying to stick to these simple colors.
Okay, let's take the red line. That's
I can
near
see
700.
like 15.
What wavelength is that?
Which red line? There's a lot.
The brightest one I can see is 690.
That's
Yeah.
right. Let's get that down at 690.
Mark it as red.
It looked kind of like a hot pink kind of color to me.
Yeah, it's partly because of the faintness.
That's what I'm thinking. It's probably just because it's going through the camera and then everything and then, you know, being feeded back over here. So I feel like the colors are just slightly off.
With my naked eye, it looks red, but it's hard to see. It's amazing. The camera is actually more sensitive than my eye. With my eye, I have to really struggle. It looks wicked red, actually, to my eye.
Okay.
We'll use red then. Okay.
Yep. Red. So that's part of it is the artifact of the camera. That is light. Okay, so let me hold this up again.
So we said 690.
Yeah, I think that's what we said. Because
Yeah.
it was like almost at 700.
690.
Okay. So like in between the
Can you guys see that orange line right at 600? Let me get this back on here again.
orange.
Kinda, yeah.
It looks more red, to be honest.
Yeah, same here. It doesn't really look orange.
Yeah, the one to the left looks definitely pink. It doesn't look red.
With my naked eye, it looks pretty orange. I wonder if I have another Mercury, because this Mercury is kind of sucking. Let me just. I don't like the way it's changing colors in here. Okay, this is another Mercury. The symbol for Mercury is Hg. Let's see if we can get a better jobby out of this.
So how did the manufacturers make mercury go into gaseous state?
They produce mercury through some chemical process. Then they do some kind of a volume gas thermometer, and they push the mercury based on density into the glass tube. This will only produce an emission spectrum if the gas density is very, very low. So that this is a partial vacuum, and the density of the gas in here is way, way, way lower than the air surrounding us. But part of the thing that sucks is there are cheap ass pieces of shit made in China, excuse my French. So what happens is because there's such an intense pressure gradient between the vacuum inside and the air outside, air tends to leak in and the gas leaks out, and that causes contamination. That's why I'm looking for a fresh one that hasn't been as contaminated by air. I suspect we'll get a, let's see. Notice how much brighter this. Whoa.
Wow.
And the center isn't purple anymore.
Right, it's just completely blue.
Yeah, let's see how this looks through our spectroscopy.
You could see it going up through the bottom.
Yeah, it's kind of.
If you had it at an angle, you could like see it flowing.
Yeah,
I wish we could have been.
that's what's happening there is kind of cool. Basically, a gun of electrons. Electrons are firing into the gas, and as they smash into the gas, they kick the electrons up to high orbits, and then the
Yeah,
high
it's like moving. I can see it like the light moving inside the
Yeah.
bulb.
yeah, it's like flickering. It's like gas flickering. It actually
Yeah.
looks pretty fucking sweet. All right, so let's go to 2.5. Let's see if this looks any different here. All right, let it focus.
I don't see any red now.
It's there. It's just.
Oh, yeah. It's
There it
popping
is.
in and out. But definitely the greens and blues are more prominent.
Yeah, this one's even more contaminated by air. Can you guys see how it flashes sometimes and you can see all those other little lines?
Yeah.
That's the spectrum of air contaminating it. Air has tons and tons of lines. We just want the really bright ones. Let's go for that one. Do you see that one that's kind of sea green? What's the wavelength?
The one in the middle?
Yeah, it's kind of like 545 maybe.
Maybe 550. No, it's below the tick. So probably, yeah, 545.
No, try again. Oh, and the bright green is 545. What about the green yellow next to it?
Oh, my bad.
90?
Mm,
Oh, 580?
Yeah, okay.
60?
Mine's 575. Okay, so let's grab a kind of light green. Hold on. I'm kind of getting into this today. Normally, I don't really care so much, but since you guys are getting into the colors, it's making me get into the colors. This is a kind of lighter green. So I'll use a light green okay, first of all, earlier I saw a very faint orange at 600. So drop it in there for fun. All right, there's a faint orange at 600. Now we saw a really, really dark and intense green at 545. So I'm going to put it almost at 550. That was a very, very, very bright green. And then we could see this kind of sea green somewhere around 575. I'll just put it over there somewhere.
Where again? The third one? The third one?
545, 575.
Okay.
600 is orange. I really should try to snap a photo of this is what I should do. Then we can just kind of look at the whole damn thing at once.
That's what I was thinking about, but it might be kind of hard to take a screenshot because the way you're holding both of the things.
One hand is holding the phone, the other hand is holding the spectroscope. So it's like
Yeah.
hit the damn button at the same time. Well,
It'd be nice to just kind of like, I went to third arm and then go get a surgery and there's the third arm.
yeah, I know. I need to drink some nuclear waste or something so I can Ninja Turtle that situation. Okay, hold on.
So, by the way, when the excitement state of electrons on the hydrogen atom, when it drops a lot, like from, I don't know, level 5 to level 1, it showed a wavelength of like 121 nanometers. So that's radiation.
That photon is emitted in the ultraviolet. I'm going to cover that next time.
Ah, there was ultraviolet. Okay.
That purple line kind of looks like 440.
That's a really beautiful violet right here.
Right.
Oh,
Those are some good pictures.
Nice.
We can look at that, right?
That's a nice
Look
one.
at
Yeah,
that.
that's cool. Doesn't this stuff look awesome? Okay,
Yeah, it
so
Got a lot more colors now.
it looks like, all right, we got a purple at 400 and we got another purple at 430.
We can mark them as the same ones, right? Because
Yeah, it doesn't have to be too perfect. So there's one at 400. Oops, sorry. And there's one at 430. And let's see, I'm going to do these last two by eye just to get a second opinion about it. So here's me. And I'm going to try to get up here and look at this thing. All right. So I see a violet at 400. The line at 430 is actually kind of an indigo. So if you have indigo, that would be good. And besides that, there are some faint greens. There's a faint blue at 440. 470 and a faint green at 510.
When you say faint, do you mean like a light green and blue?
I mean, the lines have different intensities.
Yeah.
You can see that when you're looking at them. Some of them are really bright and some of them are dim, and the intensity of the line means something. It means how probable the transition is. People actually study that stuff. So when I say light, I mean wattage, I mean intensity or brightness of the light. So I'm going to take a green and I'm going to put a real light green at 510-ish. I'm going to make it light, okay? And I'm going to take a sky blue, and it was somewhere around here at like 580 or something. And I'm just going to kind of make them faint.
Well, the other ones are at 550. Wait, is this still Mercury?
Yeah.
Oh no.
All right. Well, you might have to erase this.
I feel you. I almost messed up too. I had to double check.
This is what we have so far.
Yeah, I put a tick on neon underneath by accident, so.
Well, you might need to keep that tick there. Wait till you see neon. Neon's crazy.
Okay.
In fact, I need to shut this down.
We had a light blue on Mercury, right?
Yeah, hold on. Let me, here, why don't you?
Yeah, it was at 580.
That's like right.
All over the place. I don't even know.
3, 4, 5,
My color pattern might not be as
3,
accurate.
4, 5, 6, 7.
That's okay. As long, look, I'll only get angry if I see you put red near 400. If I see you put green near 700, then I'm going to get pissed off. But I'm not going to. I'm not going to fault you on whether you did a chartreuse versus lime green. Okay, like I'm not going to do that to you.
All right.
It's got to be close, not perfect. What color do you think neon's going to be?
A lot of colors that I don't have.
Exactly same.
Come on, you guys. I know you've been to the farm before. You've seen the Michelob sign. What color's neon?
They speak in Spanish in these colors.
My guess, a completely uneducated guess is, I don't know,
I want to say yellow. but
orange, orange, whatever.
I think it might be green.
It's red.
Orange.
That looks more orange, like an orangey red.
Yeah, that's like I was
You think about the
closer.
neon signs that you see at a bar, right?
Yeah,
Yeah,
but
exactly. Neon
yeah,
red.
but like, a lot of times people kind of I don't know, dilute the science. Maybe they call it neon red, neon blue, but neon blue is not real because
Yeah, well, there's two different
neon is
ways.
not blue.
You can use neon gas and then change the color at the surface of the glass, or you could use a totally different way.
Wait, so is this like, when we think of neon, like, is this like the default color of neon?
This is the default color of neon.
Okay.
And you see a neon sign at the bar. Okay, look at all this.
Wow, wow, I will not be able.
There's like the smallest bit of green.
Yep.
There's
yeah.
like every. I don't even think my pencil is sharp enough for that.
Hold on, we can do this.
Yeah, we can just like draw a red rectangle.
No, you can't. And here's
Just
why.
color it all in one section.
The spectrum of neon is lines. It is not a continuum. I care a lot about this. You cannot make a rectangle. Whoa, this is trippy. Because these are discrete lines, just as the electrons have discrete jumps. What we're going to do is we're going to be quantitative about this, okay? So let's find one that's a little better in focus, like here. And let's start by noticing that we got, can you see my mouse?
Yes.
Okay. Yeah. We have two red lines, one at 700, two faint lines, one at 700 and one at 690. Let's start by getting those.
All right. So make those red.
Yep. Sorry. So one at 700 and one at 690, okay? So grab those two first.
Wait, we're in neon, right? Okay.
Yep.
Okay.
Let me delete this one because this one's not as good. Okay.
We're gonna mark the green too.
We'll get to that eventually. Okay, let's see if we can count how many red lines there are.
Oh my gosh.
It would have been nicer if we could see. I
The
think
number?
there's 1, 2, 3, 4, 5, and right around here, that's 650. So we got to do 5 before we get to 650. So
Just
from
randomly
here,
put them somewhere.
so we're just going to jam them in. 1, 2, 3, 4, 5.
Before 650. Okay.
1, 2, 3, 4, 5. We're just whacking them in there.
But not at 650.
At 650, we get more. Okay. So there's the first 5. 1, 2, 3, 4, 5. That looks like a doublet. It's 2 lines that are close together. We'll call the doublet maybe 1. 1, 2, 3, 4. And that's where 600 is, where it starts getting orange. Oh, fuck. Damn it. That's not what I wanted to hit. No. 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 Oh, no.
Oh, is
By
it
the
not
way-
working now?
Oh, now,
Yeah.
Now it's going to do the thing. I meant to hit.
Why is it working this way? Like when you close it, why is it not working again?
It's something to do with the way they designed the app to connect to this. Let's see what happens. All right, let me go back to share. I'm probably gonna have to reboot my phone. Yeah. Oh, wait. It's thinking. Wow.
Oh,
Pray to the
perfect.
spaghetti monster.
Yeah, I got lucky there. That's what I meant to do. Okay. All right. So let's put in, I think it was like 4 or 5 more. 1, 2, 3, 4. And then it starts getting kind of orange. Okay. Somewhere around 620 or 600, it starts getting orange. Now I see about, 1, 2, 3, 4, 5 oranges. It starts getting kind of yellow towards the end.
Maybe because it's so bright. It becomes
Yeah,
kind of golden.
1, 2, 3. Yellow kind of kicks over after 604. And then let's just throw in a few yellowy oranges, put in a couple of golden rods, 5, 6. And then honestly, we're just going to cheat at this point. We'll throw in a yellow or
How many
2.
I'm so confused. How many oranges?
Throw in a couple of greens. I don't know, do
Sorry.
something like that.
Okay.
And that's the spectrum of neon.
Wait, I gotta copy
Yep, that's
that. Wait, 1, 2.
5.
Oh Jesus.
And then how many yellows are we doing?
I did
Pencils aren't sharp enough for this.
That's what
a
I was
couple of
saying.
oranges, a couple of yellows. Neon has a lot of lines.
All right, let's just make it look good, I guess.
Make it work. Make it work.
There's 4
The
yellows.
best we can.
My line's like getting smaller as it goes.
I went right to the document and then they have an option on it so that you can actually draw within the document.
Oh, that's perfect. Yeah, use
Yeah.
that. Use that to your
That's
advantage.
what I'm using. 'Cause I didn't have any colored pencils, so.
That's okay. If you can use your color swatch there on your
Yeah.
program, that's cool.
And then like 3 green. Oh, yellow. Gosh. Oh wait.
Hey,
green.
Professor Britton.
Yeah.
So what music do you listen to?
I listen to everything, but I listen to, since I'm a synthesizer player, I listen to like a lot of new retro wave and kind of like post 80s stuff with synthesizers in it. I love synthesizers because it's a place where science and music meet. But honestly, depending on the day, some days I'll listen to like ambient jazz. Some days I'll listen to, Americana, folk, anything. I'll listen to fucking anything. But I listen to a lot of like synth rock and new retro wave and stuff. That's sort of my thing. That's the music I like the best. Okay. We have 2 more to do. We're going to try an incandescent bulb and a solar spectrum. So let's kill this. I kind of like to do this one because it's really bright, but it might actually be too bright. Let's see if we can. Oh, hold on, guys. I'm totally going to break something. It's just a matter of time. All right. Oh. All right. So this is an incandescent bulb. It uses a filament and it generates heat. Incandescent heats up a piece of metal. What do you think we're going to see when we look at the spectrum of an incandescent bulb?
I think we're gonna see a lot of lines because it's close to sunlight light.
In fact, you're going to see something even different than that. It's a totally different type of spectrum.
Ah, there you go. It's continuous. It's continuous.
Continuous spectrum. There are no lines at all. Let's see if
I
I can
didn't.
go a little bit off axis here. Okay. So let's see if we can take a picture of that, and then we'll get the whole continuum in there. All right.
That looks so pretty.
That's probably good enough. This is
yeah.
bright.
They're not even lines, they're just bars.
It's called a continuum. There are no breaks in the continuum. So let's start on the purple side.
So does that just mean? Oh, sorry.
Sure. Usually continuum means there's no breaks. It's smooth. So 400 is usually where purple is, and it turns into indigo somewhere around 450. So here's how this works, right? So for the incandescent spectrum, we'll start with violet at 400, and it stays pretty purple. Notice I'm doing a smooth continuum.
Didn't see it.
It disconnected again.
Oh, shit.
Yeah,
All right.
I thought you meant to do that this time.
I got a potty mouth. Okay, wait, hold on. Let's
Pray
see.
to the spaghetti flying monster.
All right, hold on.
Those flying
Is that what's
spaghetti
causing the? Did I hit the thing? What did I do? Come on. It seems to be working more often than not today. This phone's getting really, really hot. Okay.
Thankfully, yeah.
Oh no, look what I did. I'm such a
Put
stupid.
it in neon. All right, so at least we know. We didn't mess up. We didn't see it, so.
Oh, damn it. Where's that? I had an eraser here. Hold on, guys. There's this one, but I have a Pink Panther. The Pink Panther works pretty good. Oh, there it is. Okay. Ah, what a stupid idiot I am. Hold on.
I mean, if that doesn't work, you could always white it out and
It
then
doesn't
just
really matter.
draw dots.
Hey, you know what? I don't have to turn it in.
I mean, you're right.
All right. Okay. So let's try that again. So
Well,
look at the spectrum. It starts 400 is purple, and then it starts to get indigo closer to 450. So what I'm going to do is I'm going to start with violet at 400, and I'm going to make it a smooth band, a smooth continuum up to about 440 or so. And then I'm going to kind of transition into indigo, which is darker blue. And indigo kind of goes from 450 or from 440 through 450 through 460. And a little bit after that, it starts turning sky blue or cyan. In Newton's day, blue just meant cyan. It didn't mean anything else. And it stays cyan right up until about 500. You'll notice at 500, it's going to start to turn to green. That one's no good.
Guys,
Wait.
quiet, please.
So you can see right around 500, it goes from cyan to green, and it stays green all the way up to 650, 660, 670 roughly. Okay.
Wait, where does it stop being indigo? Or
Somewhere between 460 and 480. Usually 470 is where it stops being indigo. In
okay.
fact, I might even made that a little bigger than necessary, but not too much. So now we're gonna get green. Get dark green, 500. Somewhere around 540, it starts getting to a lighter shade of yellowy green. And I'd say by the time you start getting up to 560, then it starts turning into yellow. Yellow is really, really narrow. It's a very, very narrow.
Yeah, it's like
maybe 10 nanometers at best.
very sharp change.
Yeah, then it starts getting kind of orangey. Then it gets really, really orange. I'm kind of going ham here. And orange goes up to about 620 or so, and then it starts getting red. You'll notice it gets red. You can see here, it's hard to see, but 600 is still orange, but around 620, it starts getting really, really red. And then it just kind of stays reddish looking. But this is a continuum. I'm not making lines.
So does that mean that there are so many thin lines that they just collide into a continuous spectrum, or?
Very good. Yes. At some quantum level, Vladimir, that is happening. But you would need to zoom in millions and billions of times before you could see such a thing. But you are correct. At some deep down level, it's still quantum, and there still would be lines. But there's just so many. If you want to know why the continuum happens versus the lines, I can try to answer that next class. But that's not an easy thing to answer, although I will try.
All right. Looking forward to it. I tried to be a big boy and have 2 lectures going on, but I quickly realized that
It's
listening
hard
to math and listening to astronomy is not a very doable thing.
No, I mean, unless you're some kind of like super talented person that I'm not, I can usually only concentrate carefully on one
And
thing.
I'm not either.
Okay, so this is what we got so far. We got one more to do, which is the solar spectrum. Now, you might think that I need to see the sun to see the solar spectrum. But the spectrum of the sun is actually encoded into the blue sky or the gray sky of clouds. Let's see what I'm dealing with today. Do you guys see that gray-white cloud up there?
Yeah.
Now, the gray-white cloud is scattered sunlight. It's photons that have been scattered from the sun, but they keep the spectrum of the sun. Even though the photons are scattered, it scatters them all in the same way. So all we have to do is look at the spectrum of the white cloud, and that'll show us the spectrum of the sun. Let's see what we can see. Oh, this is tough. Oh, it just looked good for a second. Oh. Okay, I think I got it. I had to do a bunch of snaps there. This is not hard. I mean, this is not easy to see with the cheapo spectroscope. Okay, I want you to look at some of those pictures with me, and I want you to see if you can see something special. So at first blush, what kind of spectrum are we seeing here?
Continuum.
It looks continuous
continue.
at first, but I don't know if you can see it. They're so faint. You can see them quite clearly with your eye because your eye can detect the contrast.
You can see
But
one
it's-
in blue. And
Huh?
like light blue, there's like a single line that you can kind of see.
Yeah, it's kind of a vertical dark line. Can you see it right there?
A
Can you
little
see
bit.
that?
That was what I was talking about. Yeah.
Yeah,
I
and
can't.
there's
Yellow.
one-
Well, not
guys,
yet.
Vertical dark line.
they are threaded all throughout this. You can even see them with your naked eye, but I have a shitty spectroscope. With a better one, all these dark lines are present there. And this is what is known as the Fraunhofer absorption line spectrum of the sun. I don't want to stop my share here, but let's see if I can call this up on the internet. Solar spectrum. Yeah. Let me show you what it would look like if we had a slightly higher grade spectroscope, one that had a more powerful diffraction grating. I actually have one of those right here in my room, but it's set up for my telescope and I'm really loath to mess with it. This is what it would look like if we could just get a little bit more contrast. You would see the complete rainbow, but threaded all throughout it are these dark absorption lines. Now, I want you to pay really close attention to this because the entire rest of our class has to do with these dark absorption lines. They're so important. Look, some of them are dark, some of them are faint, but there are thousands and thousands. Look how dark those are. Now, we could just about barely see them on ours, but here's how we're going to cheat. First, we're going to reproduce the solar spectrum, okay? So let's do it quick and dirty. We'll do violet up to 440. Then we're going to do indigo from 440 to like 460. Then we're going to do cyan from 460 to 500. Just a quick and dirty continuous spectrum. Then we'll do green from 500 to 540. 540, we'll do a light green to 560. 560 to 580, we'll do yellow. 580 to 600 and beyond, we'll do a bit of orange. And then somewhere over here, we'll just transition into red. So I did that pretty fast. I hope you could follow me there.
No, we did not keep up.
Okay, well, just take a moment and take it all in. Just reproduce, okay?
I just
Yeah.
copy and pasted mine.
Fine,
You did.
that works. Now, we have to make some absorption lines. Take a black pencil or use your black crayon or whatever. We could clearly see that there was some in the blue, some in the yellow and the orange. We know that there's some pretty potent ones in the green. We're just kind of putting them in random places. It turns out that these absorption lines are in the exact locations as some of the emission lines of the other atoms. This tells us that the sun contains trace amounts of all the different types of atoms.
Alright, hold on. It's yellow.
You guys see all that?
Yeah, I'm still coloring,
Sure.
unfortunately. I'm gonna
And this
just-
is our final product.
It's not gonna be perfect. This is not.
So do these lines have to be exactly where yours are, or at least like relatively close?
Relatively close.
Okay. Because all these dots are kind of messing with my eyes, and I think I might put some in the wrong spot by accident.
Just don't put them too crazy. Like, I better not see any yellows over here. I
No,
better
no,
not-
no, I got you. It pretty much looks almost the same. I just in case.
Yeah, it doesn't have to be to the nearest nanometer. It just has to be kind of close. Yours should look something like mine, and that's what mine looks like. And that's our final product. Now you've learned about the different types of spectra. So let's label the different types of spectra that we found. These types are emission spectra. Okay. This type is
I'm supposed to be seeing something. I'm sorry.
continuous. And this type is a type called absorption. So I'd like you to label your 3 different types of spectrum: emission, continuous.
I think that the camera's frozen.
Yeah.
Wait,
'cause
it's not for mine. It's
We
not
can't
for-
see anything.
Oh, there we go. Oh,
Wait.
it's frozen again. Oh, okay.
Do you see ice? It's not
Un-
frozen on the screen.
So it's not frozen anymore, but I just can't see it. Like the numbers are cut off. Can you like move it more towards like the left?
Left? What?
Yeah,
Here.
for the
There-
thing.
there we go.
Yes, there we go.
Perfect.
Sorry.
It's okay.
So,
I just didn't understand what you guys were talking about at first.
emission. Let's see. It's so hard to write with this thing.
I bet. You might be able to use a type tool instead of a writing tool.
I don't see it.
Whatever, just get it done. Don't have to be pretty.
Oh, it's crazy.
So do you guys have all this?
No. Emission and then
Yes.
Do you want me to
Yeah.
keep it?
what 5 is what?
Wait, is there anyone who's not finished?
I'm not finished.
So I'll keep holding it then.
That's what it says, continuous.
Can I just put 1 to 4 as emission because I don't have space to do that.
Sure.
4 is 5 is continuous. 6 is absorption.
Maybe that's a little better.
Mine's just
That's the best it's looked so far.
Okay. I should have done this in the first place.
So the emission and the absorption are kind of opposites of each other.
Right. Emission happens when electrons drop from high orbit to low orbit. Absorption happens when electrons jump from a lower orbit to a higher orbit and absorb a photon. They are exactly the inverse of each other.
But how do they continually absorb? Because as you said, they are present in their excited state for about 10 to the negative 5 seconds.
Right, but think about it. There's 10 bazillion, kabillion, a million atoms, right? And all of the electrons are constantly jumping up and down. So there's so many constantly jumping up and down that it becomes a continuous stream of light at that wavelength. Does that make sense?
Yeah, that makes sense. But like, how does absorption happen then? Because if you continually jump into excited state, that means that you have to also jump down to your
Right,
regular state.
There are some jumping up and there are some jumping down, but
I suspect.
well, okay, it has to do with where the light's coming from. I'm going to explain those things, Vladimir. Just hold your horses, okay?
All right.
He's
Okay.
ready.
Yeah, all right, let me stop this because this phone is starting to catch on fire here. It's so hot.
Oh, boy.
Okay, whew, that's hot. Cool, so we had a good lab today. You guys kind of got into that and that made me get into it. You guys make me very happy when you geek out on this stuff with me. That was cool. Please turn that in. I hope you had fun. I promise I won't go over again. I don't know what happened today.
And this is number 5, right? This is homework 5?
Yep. Sorry, this is lab number 5.
5. Okay.
And we're going to do homework 5 on Thursday. And Vladimir, I can hang out a little bit after if you want to pick my brain, but let me tell you that many of the questions that you're asking are questions I want you to know the answer to. And I will be explaining them to you, but it's going to be like a Jenga puzzle where I have to kind of do one layer at a time. But I can get there. I can explain those things. Okay, I'm going to stop the recording to keep this file size to a minimum. And then anyone who wants to chat or needs stuff from me can hang out afterwards. So for the people watching later on, turn in your labs, and I'll see you on Thursday. Over and out.